before Chinese New Year. It's important because, you know, if we do the planning properly, that is what's going to happen. Okay. All right, so, okay, let us continue. We have done transistor, okay. We have done diode. These are two most important. I think I spent quite a lot of time on transistor already because it is the most important switching element in any converter. And also, I also look at the point that is a, you know, enhanced version of the transistor knowledge that you need to know apart from just the electrical perspective, but we also look at the thermal perspective. Now, I believe you all, when you all design any circuit in the future, at least at this point, you are aware of the thermal issue, okay? And you know that transistor always heat up, okay, for a reason, for some reason, all right? So we know how to do the modeling, okay, in the thermal perspective, all right? Like this one, okay? If you design this circuit, you want to know how hot is this transistor, okay? You can actually, you know, do a thermal and you can design, use this one as a reference, okay, to design your, or decide, okay, your heatsink, okay? Okay, hello. Please scan this for physical attendance. Okay, do not log into team. I'm not sure it's the same or not. I'm really not sure. You scan and see lah, because, you know. Is it the same? Anyone can tell? Is it the same? Not the same, right? You know, they just give today, you know, should be the so-called latest. Then you do not log in the team, otherwise they will assume you are inside the team when they see both lah. Okay, so we done this, okay, and also I believe in future when you design something, if you feel that the transistor is getting hot and you have no idea what kind of heatsink you're going to use, right? You can do a simple, like, you know, thermal analysis, okay, then you can decide the heatsink. And yeah, various type of heatsink. And I also show a website that you can even design your heatsink and then you send order, they will cut the heatsink nicely, send it to you. All right, so they basically, we cover all the transistor. Okay, now today we are going to move to the last one of the power electronic device, which is the thyristor. Okay, all right, thyristor is work very differently. Okay, it works in AC. Okay, switching transistor, okay, work in DC. All right, there's two main difference. So it is designed, okay, again, it's a kind of switch, okay, that you can only turn on, okay, but you cannot turn off. It can only be turned off during the reverse bias. Okay, this is the original thyristor. Of course, there are new thyristor called GTO, gate turn off thyristor, that it allows you to turn off, okay, by controlling the gate. Now we look at the so-called the original one. Okay, now the thyristor usually used in AC circuit, all right, and it is meant for low speed switching. Okay, low speed. So that means usually it only used for like 50 hertz, 60 hertz, 100 hertz, most probably less than 1000 hertz. Okay, so it works at a very low frequency, so that all those switching losses that only appear on the nanosecond, right? Won't really affect this thyristor because it's work at a very low frequency, so those switching thing doesn't really affect. So you have to be very clear when talk about thyristor. It's always has something to do with AC circuit, okay, at low frequency. And of course, it has a very high power and current. All right. So again, there is another name for the thyristor. It's called SCR. Okay, SCR stand for here. SCR. Okay, SCR stand for silicon control rectifier. It was designed, okay, for rectification purpose in the very first place lah. Okay, it was designed, okay, to perform AC to DC conversion. Of course, now it has been used in a lot of like AC, and any other conversions. All right. So that's why if someone told you, oh, we are using an SCR, so you have to understand SCR, meaning that okay, they are using a thyristor. Okay, thyristor symbol looks something like that. Eventually, it's just a diode with a gate. So the diode will not conduct, even if it's forward bias, if you don't apply a current to the gate. Okay, so that's the difference. Normal diode, it will conduct when the forward voltage reaches the threshold. All right, so but this one, even it reaches the threshold, it will not conduct until you apply a small current to the gate. All right, but once you apply a small current to the gate, it will turn on. Okay, it will turn on even though the gate current, you remove it, it will turn on. Okay, it's not like transistor, right? Transistor, when you apply the gate voltage, right, it turn on, right? But you remove the gate voltage, you turn off. That is the main difference between these two switching devices. Okay, so the characteristic, the reverse bias is exactly the same as the diode. The only is the forward bias. Now, forward bias, like I said, without gate current, it is something like that. But once you apply, okay, the gate current, it will just move like that and turn on. It will become like that. It will turn on. So it will turn on as long as your anode and cathode remain positive and negative, until you reverse it by changing the polarity, or you remove the power supply to the thyristor. That will turn it off. So that is the condition of how this thyristor, okay, behave. All right. Any questions? The condition for turn off is you apply a small current or pulse at the gate. Then it will turn on.
So the conditions are you can either apply small current to the gate, turn off, otherwise not.
To turn it off, you have to either reverse the polarity or you remove the power. Two ways. Remove the power or reverse polarity. Two-way turn off. One way to turn on is to apply a small pulse, small current. Okay. So now you can see that the thing is that it doesn't require the pulse to be forever at the gate. Okay. So in this sense, it's not really, even it's a current-driven switching device, right? It's not really taking a lot of power consumption. Okay. Okay, now, yeah, I have summarized here the thyristor turn-on condition. Okay, you have a gate current. Obviously, the gate current is a standard way lah. Okay, rapid voltage rise. Okay, this one is only at normal condition. Okay, or thermal heat can cause it to turn on unexpectedly. If the heat of the transistor or the environment, okay, gets too hot, right? The electron can break through the barrier. Because it gets too hot, the electron is moving faster and stronger. It breaks through the PN junction, it accidentally turns it on. Remember, when it turns on, right, it does not require any gate current to maintain the on. So be careful on the thermal issue. And of course, light photon strike into the junction. Okay, that is what we call, they are thyristor. Okay, the symbol looks something like that. Okay. And then they will have like, a light. It's actually a window lah, for you to strike light into it so that it turn on. Okay, so that is another type of thyristor. And of course, the other type is high voltage breakdown, which means that you put a negative and a positive here, reverse bias, right? If this thyristor can withstand 1000 watt, if you apply more than 1000 watt, it break through. Again, it will turn on. And it not just turn on, it will just damage the thyristor. Chan Hong, don't log into to team yet. Shit. Then you will assume cannot do anything already. It will assume that you're supposed to scan this for physical attendance. I cannot do anything already, yeah. Then you better go home. Okay. Okay, the gate signal should be removed after the thyristor is turned on. Okay, you can still continue to have a current at the gate, nothing wrong. Okay, of course, it will just consume the current there. Okay, it won't damage the thyristor, it will just be there. Or, like I say, continue getting current will increase the power loss. Okay, so I don't think it's a big issue for the thyristor. And then the width of the pulse gate must be wider than the time required for the anode current to raise. Okay, that means the pulse wave, right, must be long enough to turn on. Okay, usually it's very short time. You see, one cycle of sine wave, right? One cycle of sine wave is 20 milliseconds. Okay, 50 hertz okay, 20 milliseconds. Scan the attendance. Wow, like that, how am I going to teach? You all come in every minute. We got 115 students. End class already. Every minute you come here and scan, no need to class. Oh. Don't blame me if I cannot finish the class. Can already? Oh. Okay, now, as we know that if we want to apply a pulse, right? The pulse, usually, okay I think, in fact it's less than 1 millisecond it will turn on. But you see, I want to make sure it's sure on. Then half is 10 milliseconds, right? So you make sure that, it should have at least 5, it will turn on. But later we do simulation, you will see 1 millisecond or less than 1, it will turn on already. Okay. All right. So turn off condition, like I said, it can be turned off, okay, by, reverse bias, okay, or turn off the power, which will reduce the forward current. So there is condition to turn off. And the turn off will be similar to that of a diode. Remember, when you turn off in the reverse, what happened? The reverse recovery thing will happen. Okay? Because it is a diode with a gate. Okay, now, this is what happens when you read textbook. That's all. You imagine yourself how this thing, or you really do lab or practical to really understand this work. Okay, so you do more. Okay, let's do this in Simulink. Okay, now in Simulink, you can have a thyristor piecewise linear. Okay, this one is a simple version. no detail. This one you can model as detailed as possible based on data sheet. These two also, even you call detail lah, to me it's not detail lah. It's something very similar to this one lah. Okay, this one also. Okay, the difference is that this one is more towards electronic. This one more towards power system. It really depends what is your objective of doing this simulation. Let's say if you are designing a converter that is going to connect to a TMB grid, right? 3-phase. Then you will usually use this one first. Once you think everything confirmed can work already, then you want to really build the hardware, right? Then you switch to this. Because remember, this one can do thermal analysis. This one cannot. But it gave you a better idea where it's like something you don't start to buy hardware and do without confirming this thing can work or not, right? It's the same thing even in the simulation world. It will save you a lot of time. Okay, come, let's do this today. This one no more download. You have to, okay, to do this. Okay, let me just open up my one so that you all can see how this thing works. Okay, this will demonstrate how a thyristor works. Okay, let me just explain. You have a thyristor. Oh, come, scan this one. Yeah. This one scan already. Confirm. Oh. If you do it online, UCSI will assume that you are not here because this is only, they want to capture those really come physical now. Because there are a lot of students, right? They pretend they come physical, but they never attend. So we want to really know how many are here, how many are online. So next time, don't do that. Okay. Okay, where am I now? Oh, okay. Now, we have an AC source. And going through this thyristor, okay, and then we connected to a load. And this load, let me check, 10 ohm. Simple 10 ohm. And then the AC source, 335. Okay, why 335? Can anyone just guess why? For fun? 335 is Malaysia sine wave peak amplitude. When you take 335, okay, 325 and 35 multiplied by 0.707 RMS, you get 230 volt. So it's not some wattage. I simply think out 100 watt through 100 watt. So that when you do real measurement, you will know that, oh, this is Malaysia wattage, the sine wave, right? Remember, we have the peak magnitude and the RMS. The 230 watt in Malaysia is RMS. So we try to do the same thing. So, okay, 325, 50 hertz. Okay. And then what we do is that we have a voltage sensor. This voltage sensor will show the voltage across the resistor, which is after the SCR at the bottom. And on top, I put a pulse generator so that I can keep on switching. Okay, the thyristor here. And then, of course, we need to have a ground. We need to have a solver configuration. So for this switching, again, remember, just now I said, Okay, the period is 50 Hertz, right? So it's 1/50. Okay, pulse width, I put 5%. Okay, I put 5%. It can be 10%, you know. It has to be less than 50%. 50% is already 10 milliamp, remember? So I put it very, very small. Amplitude is 10 watt because otherwise too low voltage you also cannot turn on. Okay, not enough current. Okay, lastly, the most important one is this one, the phase delay. Okay, phase delay equation. Okay, this is the angle you want to shift. Is pi divided by 4, which means 25 degrees, right? Not 25. Sorry, 180 divided by 4, how much? 30. 40. 45. 45, okay, 45. So this, because it's in radian, so it's pi divided by 4, divided by your 2 pi omega, the omega, which is 2 pi f. Okay, now later we will play around that, we will know. Okay, now we run this at 0.1 second. We run this at 0.1 second, then you look at the scope. Okay, see? You will have the first half cycle. Okay, you see the pulse is here, right? 45 degree. When you apply the pulse here, it will turn on the thyristor because here you see it's still off, right? It's still off. It turn on, and the thyristor will turn on, and then go to the negative. The thyristor turn off. Okay, because it's reverse bias already. Remember the sine wave? It reverse bias. It turn off until it come back to the next pulse. It turn on again. Okay, it turn on again. All right, then it turn off. So you see what happened to this. Imagine it just like this pulse is just like a chopping knife. That will help you to reshape, okay, the positive sine wave here. You can see it's a chop off. Okay, it chop off. Now you want to see more clear, right? What you need to do is that you change this one. Okay, now if I divided by pi divided by 2, 90 degree, right? So that means I'll wait until the sine wave 90 degree, I start to chop off. Okay, now I click OK, I run. So this is the most basic application. You see, you chop off exactly half, okay, of it. Okay, but if you only apply this one with the pulse, the rest is 0, right? This all will be turned off. It won't turn on. So you are controlling. If I divided by, just now it's 4, let's say 10. 10 is 18 degree. 18 degree, very small. You almost see a half sine wave already. You see? It starts to chop off only at this point. Okay? So you can see, okay, it chop off. So this is how you control how much the AC waveform you allow to pass through to the load on the positive cycle only. Because this one, you only got one. So you only have the positive cycle that will going through. Of course, if you don't apply a pulse at all, what will happen is that you will never turn it on. Okay, and you want to turn it on every time nicely like a normal diode rectifier, right? Then you need to pulse at exactly 0 degree. Then, I mean, it defeats the purpose. You want to pulse at 0 degree, just buy a diode, right? What is the point of using transistor, and they will control the thing. Of course, it will have a lot of more realistic application, okay, when we come to the AC converter. So with this one, you can play around with the angle. Okay, you can just divide by 10, divide by whatever then you can see, okay, divide by 4 by 6, for example. So this thing actually already explained that the thyristor will turn on when there is a pulse applied to the gate. It will and after the pulse already removed, it will still remain on, right? The sine wave will on until it go to the reverse bias. So it turn off, then on again. So that will explain the behavior, okay, of this thyristor. Any questions? So let's see, okay. Please do it and show in the chat box. Wow. One name in the first page, 2, 3 names. I think the good thing is that those come physical, please sign. I don't know what to do with this also. Oh, I can't tell lah. We are instructed to do this before Chinese New Year. You don't ask me. You apply lah for official, like, I don't want to come. Okay, come.
So
let's
for
do
the
it.
For the thyristor, do you do any setup on the parameter?
I think no need. Wait, let me check. I think no need. I just drag and put there. No
need. Other than the pulse generator, then another one is the source, right?
The source, 10 ohm. Okay, the source and this one, yeah.
Okay. So the source is 325, right?
325, yes. I think my slide got right. Wait, got lah. My slide got have this information. Oh, okay. I didn't put the source power. Okay. All right. Yeah. Three to 5 and 10 ohm. So I hope that you guys can get yourself much more familiar. Now we are getting more complex circuit already. But it's still not as complex as those thermal, right? Thermal is more complex, right? So, Alsama, how can work? Still working on it. Oh, yes, we have some coming in already. Okay, Jing En. Okay, Wong Hui Guan. Okay, good. Try to change the firing angle lah. Not everyone showing the same. No fun. Okay, good. All right, consider very fast already. Good. This is the speed I'm expecting you all to do. Because speed, it's just like programming, When you go to those top company, they are not just expecting you know how to do it, but within a certain time limit they set. That's the scary part, I tell you. Really, really scary. You see, this is my very personal experience. I once interviewed at when I was in UK. I tried to look for jobs, and then there are interview call. So when it comes to the programming part, right? In fact, I look at it, I know it can be done. I know I have the knowledge to do it. But the scary thing that they say, oh, you have to do it within 10 minutes. Then I was shocked. It's really like, wow, speed really matter. So it's same for this. You know how to draw it, right? If I give you 1 hour, you can 100% make it work. But let's say I say, oh, please do this in 3 minutes, for example, you will start to panic already. Good question. Wow, finally. Got student ask. I thought, wow, everybody quiet means that they know. Okay. Wow, okay, let's see. You see, in the class, got 2 students know how to do it without asking me. So they have some knowledge. Okay, very simple. Okay, maybe I drag a simple scope. Okay, I'll drag a scope here. Okay, so double click the scope. This is very important for Simulink. Go the setup. Number of input port, chain 2 or 3 or 4. Then layout. Layout 1, 2. Okay, then apply. Then OK. Then you got 2. And then you close it, you got 2 input. All right. So this is how you make a scope with multiple input. So you see, it's important to do in the class because you don't know, you ask, I tell you. If you keep quiet, you keep quiet. If you guys keep quiet when you got problem, then no one will help you already.
Sir.
Yes.
I encountered some problem with my graph. My output graph posted in the chat box there, and then actually is not really, consistent.
Oh.
Not this one, I think. This one.
This one, Teh Pun Hong.
Yeah, correct.
Okay, let's see. Hey, why everyone can do it? Your one got funny one.
That's what I feel.
Oh, most probably is your solver.
Solver.
Okay, because when you run Simulink, right, it could be, your solver. You try to go to this modeling because you use automatic. Sometimes the Simulink are not so clever to select the correct solver so that your output will run very funny. Let's see. Okay, now variable step you use automatic, right? Am I right?
Yeah, correct.
Okay, maybe you try to go to ODE 23T. You select this one and then apply and OK and run it again. See, you get a better result. My one is okay lah.
I got the better one on the bottom, but on the top, no.
Also cannot.
The bottom one, okay, seems good.
Hey, cannot lah. You see the whole class, everyone is okay, or is it something wrong with your circuit? Yeah, you see other are okay, Oh.
I think my circuit more or less the same with them.
Your circuit more or less the same. Yeah, it's more or less the same. Wow, that's interesting. Okay lah, if really cannot find the problem, you just redo it again, or else it's most probably is your circuit problem leh.
Okay, I will do myself.
What? No, I didn't train. You also cannot. Oh, that's interesting. Got the same issue.
The Thyristor using GTO, right? Is it?
No, Thyristor is not GTO. GTO is turned off. We just use a normal Thyristor. I think you get the wrong one. It's not GTO. If you GTO, of course, it won't run properly. Okay, you should go electric. Okay, under semiconductor, electrical. And then it's not this one. This is GTO. Okay, if you use this one, sure cannot run properly. GTO is gate turn off. We are not using a gate turn off. We are using this one, Thyristor, the last one. This one or this one will do. You see, if I check one is a linear piecewise. Try to change this one.
Okay, I change now.
So you are using the wrong one, right?
Should be.
Where got should be wrong lah. You admit I don't going to minus your mark.
I know, I'm sorry. I mean, I'm changing the one.
Alamak. I mean, you look at it, you know already lah.
Okay.
Okay, Lim Kai Shen, try to see whether you, you know, have putting the wrong one or not lah. See, Fu Tun Hao, I think your one is okay, right? Oh, now you laugh at your friend, eh? Later they laugh back you. The Thyristor, you use this one. Okay, Thyristor, piecewise linear. Yes. You got a sine wave. Then wrong law. You shouldn't get a sine wave. If you get this thing, you know, you should get something like that. Now you have to make sure that, okay, is this one correct? Is it Thyristor piecewise linear? Maybe I need to put the name there lah, so that you can see. Format, show plot name on. Thyristor piecewise linear. Okay, maybe I will have a look. Why this? I don't know. So your time long, right? I told you already, I don't know. Yeah, then they show how to change the plots. It's the same. Okay. Separate one. You got the number of plot 2, layout, you select 2. Hey, don't ask the same repeating question, okay? Okay. Okay, Muhammad Faiz got something like that, not proper sine wave. Yeah, correct. It shouldn't be a proper sine wave. Okay, because we want to chop the sine wave. Okay, the purpose of this Thyristor, right? You can actually chop the sine wave at a certain degree that you desire. So that is correct. Okay. Oh, not necessary. Depend on what is your intention, you know, to have a proper sine wave or not. Okay. Because this is just to show how the thyristor works. Like I explained, the condition to turn on, the condition to turn off. Okay. Now let us continue. So after we done this, so it will give you already the idea, okay, of the condition. You assume that all these pulse is just like a chopping knife, right? You move the chopping knife, okay, in the angle and you chop it off, right? 90 degrees, you chop it half lah. And the more you move, right, you eventually, you know, going to turn off the thyristor by changing the phase delay. Okay, here. Amplitude is important, okay? If you don't have enough voltage, right, then you don't have enough current, so it will not turn on. And the frequency, okay, the period is the frequency. Like I said, thyristor usually work at the power system frequency, which is 50 Hertz, 60 Hertz, and 400 Hertz, okay? Okay, now we come on again to the switching. Now the switching is less complicated than the transistor. Remember the transistor got the turn on delay time, rise time, fall time, or whatever time, right? This one, we only have the rise time and the fall time. Okay, we don't have any of this a delay time, okay, because it works at low frequency. So at low frequency, right, all those nanosecond doesn't really matter. It's so small until you can ignore it, okay? So we only concern about, okay, the, you know, how it affects the on-state current of the thyristor. So now when we turn on, right, okay, we want to know the current. Of course, you can put a current sensor to see the current waveform, but it can be calculated. Now let's look at this example. Why the average on-state current? Okay, why average? Because, you know, sine wave, right, 50 Hertz is always oscillating, okay, at a frequency of 50 Hertz. So, okay, this is entirely from textbooks. Okay, I need to declare this. That, okay, again, frequency is 50 Hertz. Right, so don't worry, in your question, I will never ask you to calculate 1 megahertz for this one. Never happen in real life, lah. Okay, so determine the average on-state current, IT. So, okay, assume that the on-state current, the current apply, right, is 1000 amp. This is quite realistic lah, because it's used for AC, right, high power. So 1000 amp, quite realistic. And then, of course, the time is 50 Hertz, right? So 50 Hertz is 20 millisecond. Okay, then again, it will have their rise time and fall time only. Okay, it will only have a rise time because this one is very slow. It takes a longer time to, you see, the rise time is all in microsecond. And then in the high speed transistor is all nanosecond, right? So it's very much faster. So this is slower. And usually they are the same. Okay, usually you will notice for transistor, right? The rise time and fall time a little bit different in terms of like 2 to 3 or less than 10 nanosecond, right? But like I say, in high frequency switching, that really matters. But at low frequency, you know, this is so small. So it can be neglected. So let's say, okay, now how to do the calculation? Obviously, okay, the whole cycle is 20 millisecond, 50 Hertz. Then you have a on time, right? 5 microseconds. So you can see that you are basically, it is really basically a triangular. Triangular means what? You take this one, multiply by this one, divided by 2. Okay, like I say, why transistor we cannot use this equation? Because transistor is not a perfect triangle. It was some curvy there and there, so that's why this equation cannot apply. But for general estimation, okay lah. So similarly, for the rise time, 4 times, sorry. So what we'll do again, we look at this part, I rise, okay, the T1 multiplied by IT, which is 1000, divided by 2. Okay, then you got 2.5 milliamp. Very straightforward. No magic, no secret. And then on time, okay, on time is 20 millisecond, right? It's 1 cycle, all right, 1 cycle, and then you need to minus this T1 plus T2, right, which is 5, and then you multiply by the so-called total current. So you get 19.99. Also very straightforward. It's just basically you take this whole thing, whole piece of junk, right? Okay, you just minus this. Yeah. And of course, similarly, this one is the same. It's just T2. Okay, unless they are different. Some got 6 or I don't know. Okay, but this is textbook. Of course, you can find this in the data sheet as well. IT divided by 2, of course, you get the same 2.5. Okay, so I4 and I rise have the same. Now, the total average current. Total average current will be I rise plus I on plus I4 multiplied by the frequencies. And you get 999.75. Okay, so over 1000. That's your average on current. So if you divide it by 1000, there will be your efficiency, 99%. You cannot get back 1000. You get back 1000, something is wrong already. Energy conservation, it will have some form of losses. Okay, so you can see for Thyristor, because they switch at a very low frequency. Okay, so remember the switching frequency, the higher you switch, the more loss you get. It's multiplied by the function of frequency. Of course, the advantage is that at high frequency, a lot of your inductor, all these components, right, can be very, very small. Okay, that's why we can have a very, you see our adapter, right, is getting smaller and smaller. But power higher and higher, right? That is because they use high frequency. But of course, we also notice that it's getting hotter and hotter. But like I say, not issue. You know, as long as you know how to have a proper thermal heatsink design and all this, you know, things still can be solved. So there is another simple equations, okay, on this, you know, like I say, it's much more less complicated because you will notice that, why there's no turn on delay and turn off delay? There is, but so small until it doesn't make a difference. It really doesn't make a difference. You know, the turn on delay is like 10 nanosecond, right, in the transistor. But this one, 50 hertz, you know, you don't really see the, you know, the difference. Okay, so the only difference you still can see is actually the rise time and the fall time. So we only take the rise time and fall time into account. So that is the second part of the calculation. Okay. Any questions?
Sir.
Yep.
Can you repeat again the rise time and the load time? I didn't get it, sir.
The rise time is the moment the thyristor turn on, right? From here to here. It requires some time, which is 5 microseconds. It does not just turn on straight like that. Straight means that the time, it takes some time to turn on, right? So this is the rise time. When you turn off, it also takes some time for it to fall from 1000 M all the way down to 0 M. So this is what we call the fall time. Yeah, fall time and rise time. Okay, am I answer your questions?
Yeah, okay, sir. Thank you, sir.
Okay, and I said this information you can find in the product data sheet. Okay, so like I say lah, yeah, your exam will be very much data sheet based. Okay, I try to make it as practical as possible lah, so that if you can answer my exam question with real data sheet, you shouldn't have any problem on designing the real, converter. Okay. All right. Now we move on to TRIAC. Now, just now, Thyristor, as we know that it's a diode with a gate control, so that you can control when you want it to turn on. It's not decided by the forward bias voltage anymore. Okay, decided by the time where you apply a pulse to the gate. But the problem is that it only, just now in our test, it only passed through the positive cycle, right? But we know that in AC, we need the negative cycle. So how? Okay, so of course the industry had come up with bidirectional triode transistor. A more common industrial name, they call it TRIAC. Yes. If you go to Jalan Pasar, you say, I want to have a bidirectional triode transistor. Most probably the guy will stand there and stare at you like, where you come from? Which university? I don't know what you're talking about. Okay, but you say TRIAC, they will say, oh yes, no problem. Which one you want, they will get for you. It's important to know the language of the industry and the language in the research community. They talk different language. So in future, if you want to do postgraduate, right, learn to talk in the research language. If you decide to go to the industry, learn to talk their language. It's not the same. That's why for experienced engineer or researcher, the moment you talk to them, they know your level, really. You talk to them and say, oh, this one fresh grad. Only fresh grad will talk something like that, So it's very important, not say just fresh grad lah. Maybe say, okay, you are just a normal student, graduate with a CGPA 4.0. You see why interviews are so important for nowadays when you want to do postgraduate study. Because everybody is 4.0, right? Then how to choose? Most important, they talk to you. The moment you give them the answer, right, they know already. This one know the difference between research language, industrial language. I will take this candidate. Why? Remember, in research and postgraduate, writing research paper is ultimate goal. If you don't know the language, you use a normal English to write paper, I really wish you good luck. It's a very common problem many of the students is facing if they are not trained properly during their undergraduate final year. They just use normal English to describe technical stuff, Of course, you get into trouble. Okay, let's come back here. Okay, so TRIAC can conduct in both directions. Okay, so it can consider as two thyristors that is connected in anti-parallel with common gate connection. Now you see the word anti-parallel. Normal English that they will connect in opposite direction, right? Then I will know, you don't know this word, yeah, you are newcomer. Okay, now this is another test. Of course, in terms of symbol, it look like that. Industrial symbol, when you go to buy, you want to draw, it's a 2 diode connect with only 1 gate. So basically, when you open this up, right, you can construct this with 2 thyristor. You can construct this with 2 thyristor. You can see anti-parallel, parallel, okay, but in the opposite direction. Okay, so you will have both the first quadrant and the third quadrant. So that is the purpose. Okay, that is the purpose. Okay, so now the thing is that in MATLAB we don't have direct TRIAC. In MATLAB there is no such thing. You go and find the library, find the entire MATLAB, no such thing. Shit. Your final year project is to design this. So fail already, because MATLAB don't have. Of course not. That's why fundamental knowledge are important. If you have the fundamental knowledge, you can create things that does not exist in MATLAB. Very, very important. This is a very important ability and skill, okay, for you to do much more advanced project. The problem with current undergrad students is that they're so rely on software. Software God, I can do. Software don't, I cannot do, right? So they are so rely on this. Okay, so that means they are limited by the software. Okay, so like I said, a well-trained student with critical thinking and skill, you should not be limited by software. If software cannot do, you create them. Okay, that is the quality. Okay, most of the postgraduate interviewer or supervisor are looking for. The ability to create. So you are telling them, no worry, if there's no such software or block in MATLAB, I create lah. Wow, if got such student, I like it. Come. Wow. You say, sir, I can only do whatever MATLAB. Other than I cannot do, I say, you better go far. Something like that, okay? But of course, this thing doesn't just come by. It requires training. So I will take this opportunity in PowerE and try to teach you how to do that. For certain part lah, for cannot all lah, right? Even, Okay, these are all this bullshit. We skip the bullshit. Okay. All right, now you can see here, creating a TRIAC in Simulink. Now I can create a block here that is belong to me, that every one of you just download, you have your TRIAC. So how to do that in Simulink? Okay, time not enough. You guys want me to continue? It's raining outside, right? Online? Or you guys tired already? Okay. No comment, so I will continue. Okay. Now, again, you see you always have a source. This one is the same, the one that you created just now, 10 ohm, and this one same. That's why I said, when I ask you all to do this, you better do it. If you just sit there and don't do, now when I move to the second part, it requires the first part, right? You cannot do, then you skip. Then I tell you, none of the converter you can answer in my exam. Then don't tell I don't teach you all. Because I cannot start from, ask you to create very complicated at once. You always start simple, then add a bit. So from here, you can see inside, right? It's a small thyristor, okay? Maybe I will show you how it is done. Okay, I will show you how it is done. Okay. Now, when you want to create a blocks that had a function of these two so-called, or whatever you can create battery or EV car or airplane, it really MATLAB can do that. I really love playing with creating something inside MATLAB. I really enjoy it. Your half cut Okay, then maybe I show you one very simple example because this is already created. So I show you the step now. Okay, I drag this here. Oh. I3 sorry computer very old already. Okay, I did 2, right? Okay, so what I need to do is that I just need to rotate this okay. You can rotate or flip okay, I just rotate it So I just rotate. Control R Oh, good, you know the secret. Okay, then you can actually do the connection. Okay, then let's say I just simply where's my register? Okay just a quick one example only You know how to do that. You connect. Okay. Let's say I just simply connect. This is the wrong one. Don't follow. I connect like that. I just want to show you if I want to make this block, right? Okay. A blocks. Okay. Okay, I still need to connect this. These two. Let's see. See, once you get it done, you double click, you can actually, see that this is, it can be connected in this way. Okay. Now you can, of course, you can use this to make the port also can. Okay, but usually I would like to connect in a way that no right or wrong. It's just like, I want to connect it like that. Okay. Then let's say, as long as you make it, because, okay, of course, you want to make it neat, right? Then you have to arrange it later. Okay. Now I want to have the utilities. No, not utilities. Here. Okay, this one, converter. Because the Simulink come here, right? Hey, is it wrong one? Oh, I need to connect this first. Okay. Let's say now you see that we need to have like 3 output, right? One is the gate, this one is the gate, this 2 is the input and output. So what we need to do is that right now, you plug it together. Then you see, it will say create subsystem. Then you will see that it become a blocks. Okay, so you can remove all this already. So it become a blocks. Okay, so this is your gate, and this is one of the input and output. Now, of course, when you want to look inside, right? You double click. Okay, you can see it actually created this. You can move them around. Okay, yeah. You can rotate them lah. This one you can, you know, this one is auto set for you, so that it is. Let's say you can flip it. Okay, now you can flip it, or you can find this connector. Okay, this connector. Wait somewhere here. Connection port. You can add this connection port if you want. Okay, if you want to do it manually, okay, you just add the connection port lah. Okay, then you connect them. Okay, but I don't know. You know, you can put a port name left and right. You can decide. Okay, so now this is done. Okay, so what you need to do is that that means you need to really create a diode here before you block them. Once you block them, right, it becomes this box, right? That means when you create this, right, you have to create this first, and after that you block them. Okay, then it becomes something like that. Then after that, you will need to add a symbol, right? Okay, so this one you need to find your own image. Right click, mask, edit icon, image. So I already have an image called TRIAC JPEG. Okay, so you can browse. Okay, you can browse your TRIAC. Okay, any small picture that will represent this. Okay, so then you click OK. Then you put your face, it will appear here. It's just an image You just put your face, then you know, yeah. So your face will appear here. So this is just a graphic symbol because Simulink don't have it. Okay, Simulink don't have it. And of course, if you decided not to make it right, you can actually unblock it There is a way I also forgot already how to unblock it. Look under the mask. Okay, this is one. Look under. There's a way to. Where is it already? Anyone know? Unblock. Where is the unblock? Arrange. No. It's not mask. Show block port name. Sorry, I can't recall it. Okay, there is a way to just remove the block so that you can actually, you know, make it like this one again with all the connected. Okay, okay, maybe I just copy out. Really, anyone know how to unblock this?
So maybe there's only online say subsystem and model reference.
Subsystem and model reference. Expand sub. Okay, create. Okay, expand. Okay, it should be this one. Try see cannot not. Cannot leh. You can remove the mask. Okay, I want to remove. Oh, okay. That means because I already put the picture there, so I remove the mask first. I clear the picture. Okay, now it become back this one. Okay. Good. Then I went. Oi, still cannot. There is a way one. There is a way one. For sure. Create mask from. This is what I create I drag and create Expand I don't know So long I never use this anymore There is a way when it will just make this disappear and create back this. Okay, maybe the good way is to not the good way This is not the proper way because to be very honest, I really forget how this thing can work. Okay, so what I will do is that I will just the best thing you all know how to do, cut and paste. Okay. Like I say, you see, there are so much to learn. Even I have been using MATLAB for almost more than 20 years. Still a lot. Every year I got something new for me to learn. Oh shit, can never end one. Okay, so you can just, create this one first. I mean, when you create this, right? Now let's say because you don't know how to create block so you just create this first. Okay, So this one will come here. Okay, I think this one is easy for you to see. I just move them closer. Okay, maybe higher a bit. Okay. So that's mean this should be the right way of doing it. Meaning that you create everything already, confirm it works, then you just highlight them and make it a block like this one. Okay, so now we don't do this first. I delete this one. So it's two-sided, right? Everything is the same, then we run. You have to make sure that it's confirmed, then only you. Okay, so one, it is done. Double click. Now you can see I can chop off the positive, I can chop off the negative. So what's the difference with the pulse generator? The pulse generator now, the only difference is you need to change the period to 100. It's no more 50 because 50 Hertz, it only chop the positive cycle. You need a negative cycle to be chopped off, right? So it's positive and negative. You double the frequencies. So it's 100 Hertz. The rest is the same. The rest is the same. So with this one, now it will show you that, now the Thyristor, you can control the power. You see, if you have full sine wave go to the load, you get full power. Now I chop this off, I get lesser power to the load. This is how you control AC power to resistive load. Okay, so now, like I said, if you change the duty cycle, not duty cycle, the phase, to divided by 3 or divided by 2, then it start to chop off more. Okay, it start to chop off more, right? And you want more, you just, or you want less chopping, then you make 10, then you almost see a sine wave. You almost see a sine wave. Okay, something like that. All right. So let's say, confirm. Wow, this one already worked as this TRIAC already. Okay. So you want to contribute. Say, okay, I want to make this one so that those doing MATLAB, they don't need to have hard time for doing this. So you just block it together, create subsystem. Here you go. Then of course add your face whatever then it become, then you just save this one, cut and paste, you email your friend can use this block for your assignment. Then you pray very hard that I don't know. Do you think it's possible? Don't worry, I'm very busy one. Usually I say, okay, full mark, go. Pray very hard that you don't know. You want to screw up your friend also can. You say, don't worry, bro, I help you. But you remove certain parameter, he can never get the same result as you. Also shit. Then he cannot blame that you didn't help him, right? I help you, I create a block, I give you all. Whole class, you only got right, bro. Or you change the internal. Shit. So you're 90 mark, he only 60 mark. He cannot blame you, didn't help him. Okay, come, class. Try to do it. I know it's already 6:30. We'll spend a little bit more time. Bong Tun Hao, wow, I like you, man. Wow, Teh Bun Hong, finally, your one work already.
So I actually did try the expand subsystem. Actually, it works.
Oh, yeah. Oh,
yeah,
good.
I actually.
I don't know why one didn't work lah.
Oh, because I'm not sure, but my one is working actually. It expanded
okay
out.
Can, no problem. Because I remember there is such function before. Okay, so never mind. It's good that. Hey, apa ni? Something wrong lah, oi.
No, sir, I haven't do it.
Wow, you this one, your Thyristor, wow.
No, sir, I haven't do. I just try the subsystem.
Oh, just for fun lah.
Just to verify the availability.
Oh, okay, no problem. Let's see how our other student is doing. Come. At least shows a few here. So I confirm that at least one student can do it, then we can happily end the class. This technique is very important for you to create something that is not inside MATLAB. Okay, and also for you to make a very big complicated system into a much more simpler system. This block is multi-layer. You can have block within block within block. Very layer inside. Especially when you're creating this very complicated system, right? Yeah, it's important. And then a lot of all these MATLAB blocks, right, is actually not done by MATLAB themselves. It's done by just user who do it, put it on MATLAB file chain to share for everyone. Until it's so good, MATLAB actually bought it off, and then put it inside MATLAB. And you will be very proud, this is what I designed one, something like that. Okay, awesome. Wow, no challenge for you lah. Good. Okay. Okay. But this is not a real blocks lah, because real block is should be one. You shouldn't see inside lah. Okay. Well, I believe you already understand the basic concept lah. Who Ziyao. Okay. Ziyao and Wong Hui-Guan.
I did with the expand subsystem, so it kind of expand out to show.
Okay. The express. Okay.
Yeah, if you don't expand, it become the normal block.
Okay, good. So at least now you know that how you can, create a component that is. You see why MATLAB don't do it, because you guys should know how to do it yourself lah. In other words. Okay. Continue. Okay, one comment, you see when you all create blocks like that, you try to rearrange, what is the input and output lah. You don't all put together like that. It doesn't look good lah, I would say. Okay. Thyristor you got one in, one out, and one control. Okay, so you can actually control this by changing, here. You can change left and right. Now it's right, if I change left, right, I click OK. So this is what happened, see? So it doesn't look good. It depends on the system or component you are creating. If you want the transistor to look something like that, then you have to rotate it lah. Okay, so you can play around, like for example, this one you can change left to right and change the port number, the name, connection, whatever. Okay, understand? Hello, Chunying. Okay, Huan. Okay, Huan. I expect you to do the block of Huan. Okay. Oh, what happened to your sine wave? Something is wrong here. Something is wrong here. Go and check whether you get the correct one and your block. Okay, like I mentioned just now. Okay, Tan Kai Hong. Also something wrong here. Same lah. I think it's a solver problem. Okay, Tam Jun Get. Tam Jun Get. Jian Te. Okay, very good. Okay, Matthew. Okay, good. Just make it a block lah. All right. Okay. All right. So that will give you the. Okay, I shouldn't save. The idea of creating a component or subsystem, okay, for simulating where there are no such component. So it's for you to you know, have your own creativity lah, of any system. Okay, that require this. Okay, almost done already. Oh, TRIAC. Oh yeah, almost already. Okay lah, this one I think we next class already. TRIAC should be very fast because we are already at 100 slide, 1115 slide. So guarantee that this Thursday can finish this chapter. And then it's a challenge for me to choose which one to come. DC or DC-AC, I also don't know. I have to think. Okay, any questions? Oh, no question. Okay, so like I said, okay, by this Thursday we should be able to finish one chapter already. So this chapter took us 3 weeks, you know. Wow. So another 3 weeks, if each this 3 weeks, 12 weeks. Wow, 14 weeks cannot finish, right? Okay lah, should be able to cover all lah. It just need to see how fast I'm going to deliver this course lah. Okay, so if okay, Juan, finally you come back with your blogs. Okay, cool. Okay, Ching En. Ching En, I'll say, okay, no problem. Okay. All right, so any questions? So if no question, then we will end the class today. I'll see you again this coming Thursday. For those who intended to stay online, please apply through proper channel to get approval, especially those who already have their own plan for Chinese New Year for the next 2 weeks. You know, just make sure that you know, for me, I'm okay actually. Okay. All right, so if no question, okay, then I will end the class today. Thank you.